Hello everyone and welcome to How-FixIT. 3 years have passed since my first video about liquid metal. In that video, I used liquid metal on my laptop continuously for 4 years and then proposed a new experiment, applying liquid metal in 2 short interval steps to form a copper-gallium surface layer. I assumed that this method could help the liquid metal stay in a liquid condition for a much longer time. So now, 3 years later, it is finally time to check how this experiment ended. Just to clarify for those who did not watch my first video, I bought this laptop in 2019 and immediately applied Thermal Grizzly Conductonaut liquid metal to the CPU and GPU. After 4 years of use, I serviced the liquid metal again during the filming of the first video. In total, this laptop has been running with liquid metal for 7 years. And yes, it is still working perfectly. You can see the laptop service tag on the bottom cover. This service tag can be used on the Dell website to check when this laptop was originally shipped to me. I have been reading your comments, and I know that many people are skeptical about liquid metal, and that is understandable. Liquid metal does react with copper, and it must be used very carefully because it is electrically conductive. But at the same time, there are many videos and opinions online where people do not fully understand what liquid metal actually does, and this creates a very misleading impression. So I want to make my position clear right away. I am not trying to convince everyone to use liquid metal. I am also not saying that everyone should avoid it. I am simply testing it in real conditions and showing you the result. The choice is yours. The only thing I can say from my own testing is that liquid metal has much better thermal conductivity than regular thermal paste. I confirmed this in my own thermal paste comparison test, and you can find the link to that video in the description. That is the main reason why I decided to use liquid metal in this laptop. So, after removing the heatsink, we can see that after 3 years of intensive use, the liquid metal has lost its liquid state again and turned into a dry metallic powder-like residue. This is clearly visible both on the heatsink and on the silicon surface of the CPU and GPU. Now, let's figure out why this happened. The first reason is that bare copper continued to absorb gallium. Even after the short interval reapplication, some gallium could continue reacting with the copper surface. The reaction probably slowed down, but it did not completely stop. And over 3 years, under constant high temperatures and heavy loads, this was enough for the liquid metal interface to gradually lose part of its liquid phase and turn into a more solid, powder-like metallic residue. The second reason is temperature. High temperatures accelerate this process. This laptop constantly works through heavy thermal cycles: heating, cooling, expansion, and contraction. These thermal cycles can accelerate diffusion, break down thin oxide layers, and gradually change the structure of the liquid metal interface. And this laptop is not used lightly. I use it almost every day for heavy workloads. I edit and render long video files in 4K resolution at 60 frames per second. During rendering, the CPU and GPU are constantly pushed close to their limits. The amount of liquid metal could also have played a role, although I do not think it was the main reason. I always try to apply a controlled amount of liquid metal, and I would rather use slightly less than too much. Excess liquid metal in a laptop is risky because it is electrically conductive and can leak onto SMD components. So maybe I applied a little less liquid metal than ideal 3 years ago. If too little liquid metal is applied, then after the reaction with copper, less free liquid phase remains on the surface, and the interface may become visibly dry faster. But even if I had applied more, there is still no guarantee that it would have remained fully liquid after 3 years on a bare copper heatsink under this level of load. And now, a logical question appears. If the liquid metal turned into this dry metallic powder, why was it still able to transfer heat? Even though the liquid metal lost its liquid state after 3 years, this does not mean it completely stopped transferring heat. If the thermal transfer had failed, this laptop would not survive constant heavy workloads like editing and rendering long high-definition videos. It would quickly overheat, throttle heavily, shut down, or become unstable. So this powder-like layer was no longer ideal, but it was still a metallic thermal interface. It continued to transfer heat from the CPU and GPU to the heat sink. However, this is very important. This is not the same as fresh liquid metal. Fresh liquid metal is still the best condition. The dry residue simply proves that the interface remained functional, not perfect. Now let's talk about the copper surface. As you can see, I tried to scrape this layer with a plastic spudger, but only a small amount of the top residue came off. The rest became almost one piece with the copper surface. This happens because gallium diffuses into copper and forms a copper-gallium surface layer. But this is very important. This is not the same destructive reaction that happens with aluminum heat sinks. With aluminum, gallium can seriously damage the structure and make the material brittle. That is why liquid metal should never be used with an aluminum heatsink. With copper, the reaction is different. It mostly affects the top surface layer. It creates a permanent stain or alloyed surface layer, but it does not automatically destroy the heatsink. I do not see deep craters, serious corrosion, or surface damage that would prevent proper contact between the heatsink and the silicon dies. This means the copper heatsink is still usable, but this test clearly shows that liquid metal on bare copper should not be treated as a set-it-and-forget-it solution for 5 or 10 years. Based on this 3-year result, if you use liquid metal with a bare copper heatsink, especially in a laptop under heavy load, I recommend checking or replacing it every 1 to 2 years. In this case, liquid metal should be maintained more like thermal paste, not left untouched forever. In my previous video, I assumed that after the second application, the copper surface would become stable enough to keep liquid metal in a liquid condition for a much longer time. After this 3-year test, I can say that this assumption was too optimistic for a bare copper heatsink under heavy long-term thermal load. The second application helps, but it does not completely stop the long-term reaction between gallium and copper. So now, after a total of 7 years of using liquid metal on this laptop, I can make a few important conclusions. First, liquid metal on a bare copper heatsink should not be treated as a set-it-and-forget-it solution for 5 or 10 years. Based on this long-term test, especially under heavy laptop workloads, I would recommend checking or replacing liquid metal every 1 to 2 years, similar to regular thermal paste maintenance. Second, liquid metal did not destroy the heatsink, and it did not damage the CPU or GPU die. Yes, gallium reacted with copper and created a permanent copper-gallium surface layer, but this is not the same as the destructive reaction with aluminum. I do not see deep craters, serious corrosion, or surface damage that would prevent good contact between the heatsink and the silicon chips. Third, if you no longer want to use liquid metal, you can still clean the copper surface more deeply with Flitz polishing paste, or a similar non-abrasive metal polish. I have a separate video guide showing how to remove liquid metal residue from a copper heatsink. You will find the link in the description. You can remove most of the visible staining and switch back to regular thermal paste. The heatsink is still usable. The most important lesson from this test is simple. Liquid metal is effective, but on a copper heatsink, it still needs maintenance. And for the next part of this long-term experiment, I want to test 2 things. First, I want to apply a slightly larger amount of liquid metal to remove any doubt that I may not have applied enough last time. And second, I want to see whether this new amount will lose its liquid state again after 1 year of heavy use. This time, I will apply a slightly larger, but still controlled, amount of liquid metal to the CPU and GPU dies. Since the copper heatsink already has a stable copper-gallium surface layer from the previous applications, I want to see if this new layer of liquid metal will stay in liquid condition longer. The question is simple. Will this extra amount also turn into dry metallic powder after 1 year of heavy use, or will it remain liquid because the copper surface is already saturated with gallium? My laptop is still used under heavy workloads almost every day, editing and rendering long high-resolution videos, so this is a real-world stress test, not a short benchmark. This time, I will not wait 3 years again. I want to check this laptop after 1 year of heavy use. The result should give us a more practical answer about how often liquid metal needs to be serviced on a bare copper heatsink. Also, write your ideas in the comments. What other liquid metal experiments should I do on this laptop? For the next video, I will choose one of the best suggestions and test it in real conditions. And finally, if you are thinking about using liquid metal because your computer is overheating, I recommend watching my video, How to Fix Laptop Overheating. In that video, I show practical solutions for reducing CPU and GPU temperatures. Poor thermal conductivity is not always the main reason why a laptop overheats, so check that video before deciding what to do. That is all I have for you. You are on How-FixIT. Thanks for watching, and see you in the next video.